In this lecture, we're going to go over the conservation of energy for open systems. Like mass, energy is an extensive property, so it too is transferred into and out of a control volume as a result of mass crossing the boundary. Since this is the principal difference between closed and open systems, the control we have another energy rate balance for a control volume system. The conservation of energy for a control volume or an open system states that the time rate of change of the energy contained within the control volume is equal to the net rate of energy transfer out by heat minus the net rate of energy transfer out by work plus the net rate of energy transferred into the control volume accompanying mass flow. So to put it in symbols, we have the rate of change of energy within our system is equal to our heat transfer rate in minus our work plus our mass flow rate in times our internal energy in plus our kinetic energy in plus our potential energy in minus our mass flow rate out times our internal energy out plus our kinetic energy out plus our potential energy out. Our last two terms are the transfer of internal kinetic and potential energy that accompanying our moving flow streams. If there is no mass flow in or out, these terms go to zero, and we're back with our energy balance for closed systems. The work term in our energy balance can be separated into two contributions. The work associated with the fluid pressure as mass is introduced at the inlets and removed at the exits. This is called flow work. And then all other types of work that exists in the system. So the time rate of energy transfer by work from the control volume at the exit related to the pressure is our pressure at the exit times our area at the exit times our velocity at the exit. We can write a similar expression for our inlet. So the work in our energy balance equation can become the work of everything else plus the flow work out minus our flow work in, where work into the system is negative and work out of the system is positive. If we use the fact that our area times our velocity is equal to our mass flow rate times our specific volume, we get that our work is equal to our other forms of work plus our mass flow rate at the exit times our pressure times specific volume minus our mass flow rate at the inlet times our pressure and specific volume at the inlet. If we substitute this equation back into our energy balance for open systems, we get the rate of energy change is equal to our heat transfer minus our work plus our mass flow rate in times our internal energy plus our flow plus our kinetic plus our potential minus what goes out, so our internal out plus our flow work out plus our kinetic energy out plus our potential energy out. If we use the fact that U plus PV is defined as enthalpy, we get that our rate of change of energy in our control volume is equal to our heat minus our work plus our mass flow rate times our enthalpy in plus our kinetic energy in plus our potential energy in minus our mass flow rate out times our enthalpy out plus our kinetic energy out plus our potential energy out. And this is the other big equation for this class. This is the energy rate balance for open systems. If a system has multiple inlets and outlets, our rate of energy change for our control volume is still going to be our heat minus our work, but it's going to be the sum of what goes in minus the sum of what goes out. We can also express things in terms of our local properties, where our energy of our control volume would be equal to the volume integral of our density times our specific energy. But again, this is not something we are explicitly going to use in this class. So we're going to look at analyzing control volumes at steady state. Again, if you recall, at steady state, we have what comes in with our mass flow rate means our mass flow rate must equal our mass flow rate out. So at steady state, our energy rate balance becomes 0 is equal to our heat transfer minus our work plus the sum of what comes in minus the sum of what goes out there's many applications that we're going to cover that only have one inlet and one outlet. If we only have one inlet and one outlet, our mass flow rate reduces down to our mass flow rate in is equal to our mass flow rate out, which is just equal to our mass flow rate. And our energy rate balance becomes Q minus work is equal to our mass flow rate times H1, our enthalpy in minus our enthalpy out plus our kinetic energy in minus our kinetic energy out plus our potential energy in minus our potential energy out. Again, assuming 1 is our inlet and 2 is our outlet. So we're going to look at a quick example where we have at steady state, we have air at 200 kilopascals and 325 Kelvin. Our mass flow rate is 0.5 kilograms per second. It enters an insulated duct having a diverging inlet and exit cross-sectional areas. The inlet cross-sectional area is 6 centimeters squared. At duct exit, the pressure of the air is 100 kilopascals and the velocity is 250 meters per second. If we neglect kinetic and potential energy and we model air as an ideal gas with constant specific heat, we want to determine the velocity of the air at the inlet, the temperature of the air at the exit, and the exit cross-sectional area. So we know that our mass flow rate is equal to our area times our velocity times our specific volume. If we use the ideal gas law, we know that our specific volume is RT over P, which means that our velocity is equal to our mass flow rate times RT over AP, which means that V1 is equal to 0.5 kilograms per second times 8.314 over 28.9 7 kilojoules per kilomole Kelvin over kilograms per kilomole times 325 Kelvin divided by 6 centimeters squared times 200 kilopascals, and correct our units of 1 meter squared. It's 100 squared centimeters squared. And we have 10 to the 3 joules per kilojoule. And we have 1 kilopascal for 10 to the 3 pascals. We get our velocity is equal to 388.6 meters per second. You always want to double check your units. The next part of the problem wants us to determine the temperature of the air at the exit. And since we are assuming constant specific heats, delta H is equal to Cp delta T. So when I write my energy balance, I get 0 is equal to my heat transfer minus my work plus my mass flow rate times H1 minus H2 plus 1/2 V1 squared minus V2 squared plus G times Z1 minus Z2. The problem states that there's no change, it's well insulated, there's no other moving parts, and we can neglect potential energy. So we have 0 is equal to Cp of T1 minus T2 plus 1/2 V1 squared minus V2 squared, which yields that T2 is equal to T1 minus V2 squared minus V1 squared over 2 Cp, which is 325 Kelvin minus 250 meters, 250 squared meters squared per second squared minus 388 squared over 2 times 1.008 kilojoules per kilogram Kelvin times the fact that 1 kilojoule is 10 to the 3 joules. I get that T2 is equal to 368.9 Kelvin. To find the cross-sectional area at the exit, we have that our mass flow rate at our inlet and our exits are equal, which means that our area times our velocity over a specific volume is equal. And again, applying the ideal gas law, we get A2 is V2 P2 over R T2. If we solve for A2, we get A2 is equal to the mass flow rate at our inlet times R T2 over V2 P2, which is equal to 0.5 kilograms per second times 8.314 over 28.97 times 368.9 Kelvin over 250 meters per second times 100 kilopascals times 100 squared centimeters squared per 1 meter squared you get our area at the exit is equal to 21.2 centimeters squared. In our next lecture, we're going to start looking at applications of the energy balance for open systems. We're going to look at different types of devices and how the energy balance reduces for these different systems.